Hello, in this video I'd like to talk about how we can take non-standard models of WeCast1S and cut and paste them together to produce new non-standard models of WeCast1S. And the key idea here is that if we look at our axioms, there's some sort of locality happening. When we require our models to be closed under certain Boolean operations, that's really kind of only happening position by position. And then, of course, to be closed under forward or backwards runs, we're really only talking about what's happening between neighboring positions within particular sets. Let me show you an example of what we're looking at. Suppose that we have an omega plus 2z model of WeCast1S. That is, its first order part looks like the natural numbers followed by two copies of the integers. And we'll have a second order part. I'm just going to call it B. It's going to be some collection of subsets of the first order part, bounded subsets of the first order part. Of course, we'll have the usual notion of successor on a woozle and containment between the first order part and the second order part. So one of the things we could do is we could take this non-standard model here and cut off this piece of it so that we're just looking at this piece of the non-standard model. And this kind of makes sense, right? We have, for the first order part, a copy of omega plus z, so that's good. And then, so I'm going to describe this interval here as c comma infinity, including c, of course not including infinity, using interval notation. I'm going to have to get creative about interval notation in this video here, because I'm going to want to talk about intervals that maybe don't have a largest element. And then how do we inherit the second order part from our original model to our restricted model? Well, we simply take all of our original sets and we restrict them to this new interval. So I'm going to take all of the sets in B, and I'm going to take the intersection with this interval here to restrict them in the appropriate way, and that'll be the second order part of this proposed new non-standard model. And then we'll have just the usual notion of successor on this subset of the original omega plus 2z, and of course containment between this collection and this collection. It's just going to work the way that containment always works. So how can I show that this restricted model is in fact a non-standard model of WeCast1S? Well, we have our axiomatization for that. It's fairly easy to check that our notion of less than or equal to is immediately inherited from the base model and satisfies the linear ordering properties that we need it to satisfy. Extensionality is easy to check. As usual, we're working with kind of a concrete non-standard model where the second order part is just a collection of subsets of the first order part, so extensionality just works. Of course, we have singletons. If we have any elements here, the singleton of that element is also going to be an element of the original model. So we take that set and we intersect it with this interval, we get the singleton that we want in this model here. It's also fairly easy to check that we're closed under union and closed under difference. Every set here has a maximum element, and that's just the maximum element of x intersected with this interval. This interval isn't in this original model, but x intersected with this interval is going to be an element of the original model, so it's going to have a largest element in this model, and of course that element is still an element in this restricted model here. And then if we want to talk about running an automaton in this model, really what we should be thinking about is having an automaton where we're not doing anything up to this point, and then we start the automaton doing the thing that we want at this point here. And then the run that we produce over here when we intersect it with this interval here, that's still going to show up in this model here, and it's going to be the run that we're looking for. Same with the reverse runs. And it's pretty straightforward to delay the operation of an automaton, right? Again, we want our automaton to not be doing anything up until this point and then start and then do stuff here, how can we create an automaton that does that? Well, we'll just take our original automaton and we'll add a new input. And we'll feed into that input a new control signal. And the control signal is going to be on at exactly this point. That is, the control signal is going to be the singleton C, and that's just going to signal that we should start running the automaton. And it's very easy to take a transition diagram for the original automaton and augment it so that it kind of waits for this signal before starting. So that's a rough sketch of why this restricted model is a non-standard model of weak S1s, and it's going to be an omega plus z model because this first order part looks like omega followed by a single copy of z. And this sort of construction here really robustly generalizes. If we have a non-standard model of weak S1s and pick a concrete point within that model and just cut out, just focus our attention on everything going on beyond that point. So our first order part is going to be, well, it's going to be all of the elements of the original first order part at that point and beyond. And then the second order part is going to be, we're going to take every second order element of the original model and intersect it with this restriction that we're looking at. Then the result is always going to be a non-standard model of weak S1s, regardless of what sort of model we started with. Now, can we do the reverse? Instead of focusing on this half of our original omega plus 2z model, can we just focus on this half of the original omega plus 2z model? What I'm trying to do is I'm trying to get at this infinite cut and this infinite cut separately, right? We had one way of isolating within this omega plus 2z model just this infinite cut. So can we isolate within this original model a structure that has just this infinite cut in it? Well, we can, but it's not going to be quite as straightforward as we might like, because this piece here doesn't look like a non-standard model of weak S1s. In particular, it has a largest element. So we're going to have to somehow deal with that. One possibility is to restrict our attention to this interval here. The standard part and all of the C plus K elements, but none of the D plus K elements. But this also isn't going to work. In our original model, we have a set that looks like this. That is, it's going to be a set that contains all of the elements from 0 to D, right? We have all of the intervals that we want, so we have the interval from 0 to D. If we tried to, like before, take all of the second order elements of our original omega plus 2z model and restrict them to this interval that we're concerned about, well, one of the sets that we're going to wind up getting is this set intersected with this interval, which is just this entire interval. And that can't be a second order element of any non-standard model of weak S1s because it doesn't have a largest element. So we can't quite do that. So here's how we're going to construct our omega plus z model of weak S1s out of our original model so that we can focus on this initial part. Our first order part, again, it's just going to be this interval here. That was perfectly fine. We had an omega plus z, and that's exactly what we want. So I'm going to use this notation to refer to this interval here. And that's perfectly fine. We're okay with that. The problem is we need to take our subsets that we get here and make them bounded somehow. We could, if we wanted to, describe these subsets as taking arbitrary elements of the second order part of the original model and intersecting them with some bounded interval on our original model going from 0 to somewhere in this second order part. Right? We have to cut them off at some point, and this is going to force all of our sets to have a largest element. At the very worst, the c plus k that we pick when we do this intersection. But I want to use kind of weird notation here in order to set up for a generalization that I'm going to do later. So what we're going to do is we're going to take our second order elements of our original model and restrict them just to this closed interval here from 0 to c. And then we're going to tack on some finite subset of this interval here from c plus 1 all the way up to this infinite cut here. I'm going to notate that by this. I'm going to say that y is a finite subset of the interval from c plus 1 up to c plus infinity. I'm describing the same collection of subsets of this interval here when I use this notation and when I use this notation, but again, I'm using this notation to kind of set up for a generalization that I'm going to do later on. As before, checking that this is a non-standard model of weak S1S is fairly straightforward. You just go through the axioms one by one and you can very quickly check off each of them. So what we had here was a way of taking our original omega plus 2z model of weak S1S and cutting out just this piece, or cutting out just this piece, and producing two new omega plus z models of weak S1S, allowing us to focus on studying in isolation this infinite cut here and this infinite cut here. And we can do the reverse. Suppose that we have two omega plus z models of weak S1S, then I claim that we can kind of glue them together to produce an omega plus z model of weak S1S. The first order part of this model is just going to be omega plus z, and here I'm just being specific about what I want to call the elements of that copy of omega plus z, and I'm calling them the same things that I was calling them before. We had natural numbers, numbers of the form c plus k, where k was an integer, and then numbers of the form d plus k, where k is an integer. So I claim that if we let this be the second order part of our model, then we get an omega plus z model of weak S1S. And I should clarify what I mean by this notation here. It's a very straightforward concept, but unfortunately we have to make up a lot of notation in order to describe what we're doing. So let's imagine that we have our two original omega plus z models here, and we have some sort of second order elements x and y within our original models. We need to somehow take these two sets here, one from our first non-standard model, one from our second non-standard model, and combine them together to get a subset of our omega plus z model. So how do we do that? Well, first we take our set from the first omega plus z model, x, and we intersect it with the interval from 0 to c minus 1. We cut it off just before c. And so I'm going to take this bit of x and copy it down here. And I'm going to cut it off just before c. And because x can be any second order element in B, we're going to get lots of freedom in how we choose this set here, and that freedom comes from how we choose our set x here. And we're really copying this entire infinite cut here into this infinite cut here. If we have some sort of tail-head pair going on in our original model, when we copy this bit over into our larger model, we're going to capture that tail-head pair over here. So we're going to get the same tail-head function for this infinite cut as we do for this infinite cut. Now what we do for y, the subset of The second order model that we're looking at here is pretty straightforward, but I'm using complicated notation for it. So what we're going to do is we're going to take this set and we're just going to copy it down here. And that's all that we're doing. Now, unfortunately, we're going to have to use some complicated notation in order to express how we do that. Because the names of the positions that we're talking about for this subset here have changed, right? Instead of calling this position here, where y starts, 0, we now want to call it c. And the next position, instead of calling it 1, we want to call it c plus 1. And then c, on the other hand, instead of calling it c, we want to call it d. And so we need some sort of function to translate from this space to this space, and that's just this function here. If the input is a natural number, we just translate it into c plus that natural number, and if the input is of the form c plus z, something over here, we translate it to d plus z, something over here. So that's all this function does, and this double prime notation just indicates that we're interested in applying this function to all of the elements of our set, to take our set and translate it into this new space here. So this is how we can take one second order element from our first model, one second order element from our second model, and kind of merge them together to get an arbitrary second order element of the omega plus 2z model that we're trying to produce. And again, the proof that this here is a non-standard model of weak S1s is really quite straightforward. You just go through the axioms one by one, and they're fairly easy to check off. So one of the things that we can do, combining the three constructions that I've talked about so far, is to take one non-standard model of omega plus 2z, cut out this bit to get one omega plus z model, and cut out this bit and get another omega plus z model, and then swap the two bits, and then paste them back together using this construction here, but swapped. And in doing this construction, we take this infinite cut here and swap it with this infinite cut here. If we have a tailhead element over here, it's going to wind up over here when we do our cutting and swapping and pasting. And if we have a tailhead function over here, it's going to wind up over here when we do our cutting and swapping and pasting. So this answers one of the questions that we had before, which is, could there possibly be a difference between the sorts of tailhead functions we can get in the first cut of an omega plus 2z model versus the sort of tailhead functions we can get in the second infinite cut of an omega plus 2z model? Is this location somehow fundamentally different from this location? Well, of course, in any one specific omega plus 2z model, they could be different. We could have two very different things going on over here and over here. But for every model where there's thing A going on over here and thing B going on over here, there's another model that we can produce where thing B is going on over here and thing A is going on over here. Or we could produce a model by kind of doing a duplication as opposed to a swapping, where thing A is going on over here and over here, or where thing B is going on over here and over here. So in the grand scheme of things, there's nothing special about this cut because it's the first cut of an omega plus z model. There's nothing special about this cut because it's the second cut. And generally speaking, thinking about this process of taking a non-standard model of weak S1s, cutting it up into parts, scrambling those parts around, maybe duplicating some of the parts, maybe ignoring some of the parts, and pasting those parts back together gives us a new model of weak S1s. In particular, when we cut up a woozle, there's two types of parts that we can have. We're always going to cut, we're never going to cut in one of these infinite cuts, right? We couldn't separate this bit from this bit here. What's going on in this bit here and what's going on in this bit here are very closely related to each other. We really can't separate them in any sort of meaningful sense. So when we do our cutting and pasting, we're really going to have to cut within one of these Z components here. And when we cut a woozle like that, there's two sorts of things we can get. We can either get some sort of interval that has a largest element, or we can get an interval that doesn't have a largest element. I'm going to want to call these sorts of intervals here end pieces, and these are just regular pieces. So if we want to be specific about how this cut and paste construction works, we can cut out of various non-standard models a bunch of bounded pieces, pieces with largest elements, and we can cut them out of all sorts of places. We could cut them out here, we could cut out one piece here like that. There's all sorts of ways of cutting out bounded pieces from non-standard models. We're going to cut out a bunch of pieces like that and one end piece. And what we're going to do is we're going to have a bunch of bounded pieces followed by an end piece, paste them all together to get a single non-standard model of weak S1s. This is kind of a useful perspective to describe what we've done already. In this construction here, where we were taking two omega plus Z models and kind of pasting them together, well, really what we were doing was taking this original omega plus Z model and cutting it off here, right? Cutting out this bit here to get a bounded piece. And then this piece is a valid end piece because it doesn't have a largest element. And then we're pasting those two pieces together. For our earlier constructions, when we took an omega plus 2Z model and restricted it to just this interval here, we were just cutting out this one end piece, and that end piece alone was going to make up our new non-standard model of weak S1s. On the other hand, the second construction that we did, where we took this piece of the original omega plus 2Z model and used it to construct a new omega plus Z model, really what we were doing was taking this bounded piece here, cutting it out, pasting it in here, and then we need an end piece to go on here. And the end piece that we picked was simply the standard model of weak S1s. We were taking finite sets of natural numbers, right? Second order elements of the standard model, and pasting them on here to sets that we got out of our original omega plus Z model, like that. So this really solidifies our intuition that when we're trying to study non-standard models of weak S1s, the only thing, really the only thing that we're interested in are tailhead maps over specific cuts. Because by applying an appropriate cut and paste construction, we can take infinite cuts from one model and move them over to infinite cuts somewhere else. And that tells us that these infinite cuts are really kind of interchangeable with each other. So now we're interested in studying the infinite cuts that we can have show up. And there's lots of different types of infinite cuts. I mean, here we're looking at really kind of the simplest thing, which is an omega plus, really we're looking at an omega plus Z model when we're looking at this cut here. We could have much more complicated things show up, but let's just try to study these really simple cuts. There's a copy of omega over here, there's a copy of the negative natural numbers over here. What can go on in the middle? What sorts of tailhead maps could we possibly get? In the next video, I hope to partially answer that question. I wasn't able to totally answer that question in my PhD thesis, but I was able to answer a countable version of that question. And I'll show you what that result looks like in the next video. So thanks for watching. Let me know if you have any questions or comments down below, and I hope to see you in a future video.